we're going to look at sampling and sampling distributions. So in this class, we're going to discuss what a population is, what a census is, what a sample is, and the different types of sampling procedures. By definition, a population is simply defined as all possible outcomes of a measurement of interest. A sample, on the other hand, is simply a subset of a population. We have different types of populations. There are populations that are infinitely large, so we may need to use statistical analysis. Of course, a larger sample size gives a more accurate precision. But in order to interpret the results, we need to understand the behavior of samples. And so that's the lesson, sampling distributions. Sampling distributions. We sample for many reasons, because of accuracy, time, finance, sampling errors that are attached. So we're going to look at many ways in which you can sample populations. So there's what we call a simple random sample. This is simply a sample that is randomly selected so that every combination has equal chance of being chosen. For instance, you have an urn that has 6 balls with different colors. What are the chances of picking 3 balls without looking inside the sample? That is what we call simple random sampling. When we are selecting a winner for a lotto, we use simple random sampling to select the numbers. So we also have what we call systematic sampling. Systematic sampling includes us selecting the nth number of a population. It is what we use in tithing. When we are picking the 10th of every produce we have, that is systematic sampling. We also have what is called cluster sampling, where we first divide the population into groups, which we call clusters, then randomly select clusters to include them in the sample. Now, the entire cluster, or just a randomly selected portion, may be selected. Here, as a researcher, you wish to poll a sample of shoppers at a shopping mall. So you will need to choose stores. And these stores, will call them clusters. And you interview customers from inside those stores. And when you pick those, you put them into a pool of an interview list. So this is what we call cluster sampling. Cluster sampling is very cost effective because it helps us use minimal costs on a sample population. So in this example, we talked about the mall. You don't have to know anything about the shoppers ahead of time. You just pick them from few stores and ask them about a particular product. For instance, Trade Kings want to find out how their product offering is. We also have what is called stratified sampling, where we pick populations and manually we divide them into what we call strata. These are mutually exclusive groups, meaning they don't have an intersection. You can have top management, middle management, low management. They're distinctive. So we select a sample from each of these groups because they have different information that they are confined to. So these strata that we collect have less homogeneous samples, less similar samples. So when we're dealing with stratified, you need to understand that there's a thin line between cluster and stratified, cluster sampling and stratified sampling. So we use what is called the central limit theorem in sampling distributions. Central limit theorem in sampling distributions. All right. So we're now going to look at our central limit theorem that gives us the standard deviation of a sample. So standard deviation of a sample under the central limit theorem is simply given by standard deviation over square root of n. Okay. So this sigma that we are seeing here is actually the standard deviation of a population. The n represents the sample size. So the standard deviation of the sample is formally known as a standard error. Now we use a z-score for a sample whose sample size is more than 30. So this is called the standard error. So it is when we're coming up with a z-score is given by the mean plus mu over standard deviation root of n. So you can also write this as x bar minus mean over the standard error. Okay, so let's learn how to calculate the standard error with notable examples. So here we're given a sample of 16 men who are selected in an age group. And we are told that the probability that the average blood pressure of this sample will be greater than 250 millimeters. So we are looking at an example where a symbiotic blood group of 30-year-old males is normally distributed with an average of 122 mmH and standard deviation of 10 mmH. So we're being asked to firstly calculate our standard error. So we have also been told that a random sample of 16, so n is 16 in this case, n is 16, and we are also given that the standard deviation is about 10, the average is about 122. So we want to find the probability that is greater than 125. So before we go there, how do we find the standard error? Standard error is simply standard deviation over square root of n. So here we have 10 over square root of n, square root of 16. So this is 10 over 4, which is 2.5. So our standard error is 2.5. Now we're being asked to find the probability that x is greater than 125. Using the z-score, our x bar is 125. So I gave you the formula of the z-score, which is simply x bar minus mu over standard error. So 125 minus 122 over 2.5. So 2.5 is our standard error. Then our z figure is 1.2. All right. So we will also go to learn how to read the z-score tables. Now we have tables under the z-score. We have 4 types of tables you need to know. The z-score table, we have the t table, and we also have the f table. So when we're dealing with one mean, we're using a z table, for especially samples that are greater than 30. If dealing with 1 or 2 means, we also using our t table, but for samples less than 30. But if there are more than 2 means, we use an F table where we're going to look at ANOVA. This is the simplest topic. But let me now first teach you how to deal with the Z table. And the Z table is read as follows. If you're looking for a reading like 1.23, you go under 1.2, the first two digits there, and 0.03, where they meet. The probability is what is in between here. So let's go to the Z table and check under 1.23 and see the reading that we're going to have there. So 1.2 and 0.03. 1.2 and 0.03. They're meeting at 8907. So that is a reading 0.8907. So basically, these give us probabilities of the areas under this plot. So we know that if we're dealing with a normal distribution, each quadrant is 50-50%. So this is where our 0 is. But if we're dealing with numbers that are positive, so 1.23, so the reading according to this table is 0.8907. Of course, we know that this part is 0.15, so meaning this part should be 0.3907. So if you're using a half table, it will only give you this reading. But ultimately, the whole area from here up to this whole area is called our probability of 1.23. So suppose we have a number like 1.66. 1.66. So you round off this one to the nearest two decimal places. So this is 1.67. So how do we read this one here? We go under 1.6 and under 0.07, where they meet. That is where the reading is. So 1.67, what would the reading be here? You go under 1.6, under 0.07. What is the reading here? 9525. So 0.9525. That is how the reading will be. So for instance, if we're asked to find the probability of Z is greater than 1.67, what this simply means is we are going to illustrate, and 1.67 is here. So the whole reading from here to here is 0.9525. So meaning the reading that is remaining here, the small reading here, we'll simply subtract 1 minus 0.9525. So this is what we'll get as a remainder. Okay. So that is how we calculate that. 1 minus 0.9525 will be 0.475. So that is how we read these tables. Okay. Now, these tables are very important to understand in that I will bring about principles of what to do. So if we have a shading which looks like this here, if we have a shading which looks like this here, if we have a shading which looks like this, and if we have a shading which looks like this, what comes to your mind? Shading 1 simply tells us that we are shading to the right side, which is greater. So shading to the right side means greater. Shading 2, we have a small shading here. This small shading simply tells us that our shading should be subtracted from 1. All probabilities that are positive or using that quadrant are more than 50, but this is a smaller probability, so we subtract our probability from 1. What does the shading here tell you? It simply tells us that we are shading to the right. It is also greater, but this shading that we are seeing here is a big shading, so we just read the probability directly. There's nothing to subtract from 1, because it's already 50%. This shading here tells us it is less, or less, since we're shading to the left side. However, the shading is small, so meaning whatever we're going to get there, we're subtracting from 1. This side is also left, so it's less, but it's a big shading, so meaning we're going to read it directly. So if we're given probabilities to illustrate z is greater than 2, great, z is less than 1, great, z is greater than -2, z is less than -1. How do we illustrate these ones? So we know that the z reading for 2 and the z reading for 1 as follows: 2, 0.9772, 1, 0.8413. Let's verify what is the reading at 2.0. We go under 2, under 0, this is 9772. 1.0 is 8413. These are the readings for z. But to illustrate these readings, z is greater than 2. We shade, illustrate. So 2 is here, we put our divider there. Z is greater, so we're shading to the right. What does the shading tell you? The small shading here. So when we have a small shading, what is our policy? 1 minus the probability, 0.9772. How about the next one, less than 1? Less than 1 here, we're going to do what? Illustrate. 0 is here, and our 1 is there. We put a divide. Less means we're shading to the left. Already we're able to tell that the shading is a big shading. So we are going to get the probability directly as it is. So this whole probability is simply 0.8413, because we know 1 has that probability. How about z is greater than -2? All z values that are on the left side of 0 are negatives. But because it says greater, we're shading to the right. But this shading to the right, already we're able to tell this is a big reading. So we're going to read it directly. The reading for 2 is 0.9772, and no need to subtract. How about here where it says less than -1? Z is less than -1. So -1 is on the left side. Where are we going to shade? On the left side. And as you can see, the shading is small. So what we're going to do is 1 minus the reading for 1, which is 8413. So these are the principles that you need to know when you're dealing with Z. These are the principles that you need to know when you're dealing with that. Okay. Now there's also what we call standardization. Standardization happens when you're not given the values of what? Of Z. It is simply x minus mu over standard deviation square root of n. Or as we've just learned, the mean minus mu over the standard error. So in the event where we're given, for instance, the mu is 10 The standard deviation is 3. And we are told part 1, compute the probability x is greater than 6. So we use ISA. Illustrate, shade, standardize, and apply. So let's illustrate. So we have 10 here. This is 16. Then we're saying less or greater than 16. So illustrate, then shade. We're shading based on the sign which says greater. Right? Then we standardize. How do we standardize 16? Z is equal to x minus mu, standard deviation over square root of n. So our x is 10. Our x is 16, sorry. Our mean is 10 over our standard deviation is what? 3. Okay. When we don't have our n, our formula simply becomes z is equal to x minus mean over standard deviation, just as it is. So standard deviation is 3. So 6 over 3, we're going to get 2. So this 16 is equivalent to 2. Already we know that 2, when we read it from here up to there, is 0.9772. So to get the small shading here, what we do, we subtract 0.9772 from 1. So what we get? 0.0228. So that is the shaded region, which is here. Suppose our mean is still the 10, standard deviation is still 3, and we're being asked to find probability x is greater than 7. Using ISA, we are illustrating. Our 10 is here, our 7 is on the left side. We know 10 is 0 when we standardize it. Greater than 7 to the right. Standardize the 7. 7 will be a negative because it's already on the negative side. 7 minus 10 over 3 is negative 3 over 3 is negative 1. So this negative 1, we're going to have, it's a big shade. There's no need of subtracting. So we're going to have 0.8413. So this is the big shading that we're going to look at. Sometimes we may be asked to find intervals between two shadings. The mean is still 10, the standard deviation is 3. And they're asking us to find the shading between what? 13 and 16. So our 10 is here. Our 13 is here. Our 16 is there. So whenever they're on one side, you standardize. Our 10 is equivalent to 0. How about 13? 13 minus 10 is 3. 3 over 3 is 1. So this 13 is equivalent to 1. Then you go to the standardization of the 16. 16 minus 10 over 3, 6 over 3, which is 2. So this is 2. So whenever they're on one side, you get the z for the larger number minus the z for the smaller number. So what is the z for the 2? 0.9772. The z for the 1? 0.8413. You just get the interval between the two. So we're going to have 1359. So that is the interval between here, about 13% or 14%. Suppose they were all on one side, but on the left side. So the mean is still 10. Standard deviation is still 3. Then we're asked to find the interval between 4 and between 7. So we're going to illustrate. 10 is here, 7 here, 4 is there. Obviously, this ones will give us a negative z. 7 minus 7 minus 10, negative 3. Negative 3 over 3, negative 1. 4 minus 10, negative 6. Negative 6 over 3, negative 2. Still, the large number is 2. Ignore the negatives for now. The small number is 1. So we're still going to get 0.9772 minus 0.8413. So the difference here is 0.1359. So that's the difference between the two intervals. But the tricky part comes when you're having a sandwiched interval. We have a number here and a number there. Maybe there's negative 1 there and a positive 2 there. So you just add 0.8413 and 0.9772, and the sum total is subtract 1. What we're going to get is 0.8185. That is how we calculate the intervals. So the instances where you are not given the value of x, we're still at 10 and standard deviation is 3. And we're told that the probability is more by 2%. We are told to find what? X. So when you go here, more by 2%. So you're going to subtract the 2% here from the 100%. This is 98%. When you're converting it to decimal, 0.98. We know our mean is still here at 10. Our x we don't know. But we have 0, which is z for the mean. But we know the z for 98%. We'll go into the table and look for 98% inside the table, or a number close to 98%. So we look for 0.98, which one is closest? Closest to 0.98. Between these two, 98.03, 97.98. So this one is closest. So the reading for this one is 2.05. 2.05. If I ask you what is the reading for 1.96, the z for 1.96, you go under 1.9 and 0.06, which is 0.9750. But if I ask you the opposite, give me the z for this probability, you simply add 1.96 and 0.06. 1.9 and 0.06, it will give you back the original. So whenever you're looking for figures inside, arbitrarily, you need to look, because these ones are ascending in order. So you can literally look for the exact figure or the closest possible. So I repeat here, find the value of x for which we are greater by 2%. So we're not going to cut from the left side unless it said less by 2%. So we're going to cut from the right side because of the word greater. Step 1, cut. Step 2, the 2% from 100, we get 98%. In decimal, which is 0.98. Step 3, locate this 98% inside the table. The closest we found was 9798. So what is the reading for this one? 2.05. That is a z. So z for this one is what? 2.05. So since we know the standardization formula, we just substitute to find what our x is. So z is 2.05. Then our x here, we don't know. Our standard deviation here is 10. And we have our 3 there. We'll cross multiply. Okay. So when you cross multiply, 3 times 2.05. We're going to get 6.15. When this one goes aside to add, so when you add a 10, our x is going to be 16.15. That is how we find the value of x. That is how we find the value of x. Now, colleagues, you make things seem so easy. How do questions really come? Are they as easy as you portray them to be? You need to think they are not as easy, but they are manageable. So now I want to look at an example from Introstat, where we're going to look at the way questions may come, then apply our everything that we've just discussed here. Okay, so let's go through one of the questions to do with cold drink. Help me identify what parameters are there. Let's look at this question here. What can you see? Question 20C. So second part here, we want to look at probability that the cup contains at least 200 ml cups. So,
Colin, sorry to cut you short. I think for the first part you were mute. I doubt anyone heard you.
okay. So I'm doing part B. I start from part B. Part 1, I've already finished. Have we understood how we do part 1?
I think you were muted, Collins. We didn't get you.
You didn't get how I got this figure?
There was no audio.
Oh, sorry. So let me go through it again. A soft drink vending machine has an average of 215. So 215 comes here, it's equivalent to 0. Then standard deviation is 10. Then if 225 cups are used, what proportional overflow? Overflow means greater. So we're looking at greater than 225. So 225, using ISA, we illustrate, we shade because overflow, we standardize is 225. Using this formula, x minus mean over standard deviation. So in standardize, we got 1. So 1 is equivalent to 0.8413. Because the shading is small, we're going to subtract from 1. So 1 minus 0.8413 will be 0.1587. You can leave it like that, or proportions usually are in percentages. You can simply say 15.87% if you want. The same. Then we go to second part. Part is a probability that a cup contains at least 200 ml. At least means greater, so greater than 200. The difference with this is that it's on the left side. We're still going to shade to the right side because it says greater, except that this shading is big, we will not subtract. So we illustrate this 200. So x minus mu over standard deviation. So 200 minus what? 215 over 10. So this is negative 1.5. So negative 1.5. All right, are we together so far? Any questions? So if there are no questions, we check 1.5. The negative just shows you that you're on the negative side, but you can still be using one side of the tables, which is the positive side, which I encourage you so that you don't get confused. So the tables are too many. So if you learn all of them, it will stress you so much. Just concentrate on one table. 0.9332, 0.9332. So this is equal to 0.9332. Why are we not subtracting from 1? Because this shading is bigger than 50%. Lastly, we are being asked, whenever you see a percentage, you're being tempted to read from inside the table. So what size of cups ought to use if we only want 2% overflow? So like I discussed, overflow is on the right, underflow is on the left. So 2%, what remains here, 98%, which is 0.909800. Here, it's already the 215, which is equivalent to 0. Here we don't know the x value, but the z we can identify it from the 98%. So I taught you how to read from the table. 98 is 0.9800. So this is the closest, 98%, so 2.05. So the z reading will be under 2.05. So they're asking what size of cups ought to be used. So z is equal to x minus mu over standard deviation. 2.05 is our z. X we don't know. Our mean is 215. And our standard deviation is 10, as was given here. So you cross multiply. So this is 20.5. It's equal to x minus 215. So when we take this one on the other side, our X would be what? 235.5. So how many mu caps should be used? 235.5 mu caps should be used for us to be confident that only 2% can overflow. So this is what they use in production of drinks, liquor. They have probability allowable for wastage. So I'll end here and I'll send questions just on what I have discussed with you. So we end here unless any burning questions.